Hello everyone. In this video, I'm going to talk about how to find normal and curvature for any given point cloud. So in order to compute normal and curvature for any given point cloud, we utilize the positional data of the points to do so. So let's take an example where we have a point cloud um, which has P1, P2, P3, and Pn set of points. And we take one point, which is called Pi, and we try to estimate the normal and curvature. In order to do so, what we do is that we take the k nearest neighbors for this point Pi, and then we calculate the covariance matrix for this point Pi. To calculate the covariance matrix, what we do is that we find the mean of this k nearest neighbor points, and then we use this formula where we take each and every individual point in that neighborhood, which is k nearest points, and then we subtract the difference between the mean and this nearest point. By doing this calculation, what we get at the end is the covariance matrix, which is a 3 cross 3 matrix, which represents how all the points in this k nearest neighbors correlate with each other. Once we have this 3 cross 3 matrix, which represents this correlation, we calculate the eigenvalues and eigenvectors. The eigenvalues lambda 1, lambda 2, lambda 3 are then kept in an ascending order, as similarly the eigenvectors. So these eigenvalues represent the contributions of each principal directions, and the principal directions are the eigenvectors. So for these for these set of points, the eigenvector representing the least eigenvalue is the normal. Why we say so is that for any given set of points, the two directions where there's highest variance is the x and then the y, and then the third direction is the z, which is the normal direction. And that's why we take the eigenvector associated with the least eigenvalue. Next, in order to calculate the curvature of the points, what we do is that we take the least eigenvalue and we divide it with the sum of all the eigenvalues. So this is done so that the eigenvalue, which represents the contributions of each of the principal directions, we take the principal contribution of uh, the normal direction eigenvector, and then we divide it with the other contributions from all the three eigenvectors. So what does this represent? This represents how flat or curved the local neighborhood is. A higher value, what it says is that um, it is more sharp and there are some features in that area. And this curvature is the basis to do feature detection on a 3D point cloud. And this is how we go from just set of points where we just know the XYZ to getting the normal and the curvature, which lets us to do more manipulation with a given point cloud. Thank you for listening.